Greetings and welcome, friends. Here we are, we're taking a look at solving systems of linear inequalities today. But before we even get to solving systems of these things, I want to talk about just graphing inequalities, just straight up figure out how to do that. So here's a little recall for us to consider, so to speak. So here it says graph 2x minus 3y is less than or equal to 6. So if I want to graph that, chances are you would be interested in rewriting that in slope-intercept form, y equals mx plus b, which would be convenient to do so that I know the slope, the y-intercept. And in order to do that, I'm going to solve for y. So let's see. So let's subtract 2x from both sides. And I would have negative 3y is less than or equal, right? Remember, I'm taking care of this inequality here, right? Less than or equal to negative 2x plus 6. Now, how would I solve for y? Divide by negative. Divide negative. Guys, wait a minute. I think we just said divide and negative in the same sentence when talking about an inequality. You better believe we'll flip that inequality. Bam, flip it like a pancake. Here we go. So this is what I got. Y is greater than or equal to 2/3 x minus 2. So looking at this, what is my slope and my y-intercept?
Okay, so let me break it down for you. Your slope.
Yes, slope.
Yep, it's already been broken. There we go. So so let's graph this. So y-intercept of negative 2 would be somewhere like here. And the slope of 2/3, I would go up 2 units, right? So there's 2 and over 3 units, somewhere like that. And that would be another point on my line. I also could go, bless you, down 2 and left 3. Guys, settle down. If I want to go down 2 and left 3, negative 2 divided by negative 3 is still positive 2/3. So you could do that as well. Now question, bless you. Would I expect this to be a solid line or a dashed line?
Solid.
How do you know?
Because it could equal the line.
Because it includes the equal to. Perfect. So it's a solid line. Like so. Because it could equal the line. So let's make a little note of that. Solid line occurs for the symbols less than or equal, greater than or equal sign, I suppose, if it was just a straight up equation. So that's going to be a solid line. A dashed line, which I probably will call dotted for some reason, even though it's still dashed, will occur anytime you have less than or greater than as your symbol. Okay, so have I graphed?
I hate the dash line because you can't tell it. Sometimes you dash in it and then it gets blended in with your points.
Yeah, that's fine though. So am I done graphing this?
No, you gotta scribble on one side.
Yeah, I gotta shade it. So which way do I shade? Do I shade above or below in this case?
Above.
Amen to that.
How do you know?
Because y is greater than.
Right, and greater, it's a y relationship first of all, so it's vertically oriented here is what we're talking about. So a y relationship, y is greater than, sounds like y is above, right? So we're going to shade above anytime I have a greater than or equal or a greater than symbol, I guess specifically with a y there next to it, something like that. And we'd shade below anytime I have a y is less than or equal or a y is less than, right? Less than the line would be beneath or below the line. There's one more situation I want to talk about with shading. I shade to the left. I guess I'll throw a t in there too. Why not, shall we? I shade to the left anytime I have an equation that is x is less than or equal a number. All right? Or x is less than, I suppose. And I shade to the right anytime I have x is greater than or equal or x is greater than some number. The reason I shade left or right for these x equations or inequalities in this case, I suppose, is because x equals a number would represent a vertical line, and you can't shade above or below a vertical line, right? So the moment it's x related to something, it's a horizontal relationship, so I'm thinking of it in terms of left or right. And the smaller values on the x-axis are to the left, because that goes towards negative infinity, where the larger is to the right, because that's positive infinity. So for our situation, yeah, we're going to shade this above because of the greater than sign. So I would shade something like this, right? And all of these points within this region are solutions of my original inequality, as well as hopefully this one if I didn't make any mistakes. Which, if I wanted to do a check, we could pick any old point in this region. The easiest one to do would be 0, 0. So let's just do a quick little check. Why not, shall we? Let's check 0, 0. I'm expecting this to be true, not 2. 2 times 0 minus 3 times 0. Is that less than or equal to 6? Is 0 less than or equal to 6? Is that true? Oh yeah, that's true. That's definitely true. Definitely true.
Yeah.
So it does appear as though, unless I made other mistakes, I did shade in the correct direction. So that's our little recall there on graphing a single inequality. All right, let's talk about a system of inequalities. A system. Let's see. I wonder if I should leave room on the... nah, this will be fine. So here's our first example. So I'm going to talk about graphing a system of inequalities. So I've got 4 separate inequalities here. And when graphing a system, I'm essentially going to graph all of the inequalities on the same coordinate plane and find out where their shaded regions overlap one another. The common shaded region between all of them is what we'll be talking about. So let's analyze these a little bit real quick. X is greater than or equal to 0. That's going to be a vertical line. Y is greater than or equal to 0 is going to be a horizontal line. Which way would I shade X is greater than or equal to 0? Left or right? Shade to the right because greater than? Yep. Which way would I shade Y is greater than or equal to 0? Above or up. All right. Shade up or above. There we go. Now these other 2 lines, I'm expecting these to be diagonal lines, and the first thing I'm going to do with them is put those in slope-intercept form. So this one, 2x plus y is less than or equal to 8. So put that in slope-intercept form, what should I do?
Wait, what does shade A mean?
Above. Yeah. Yeah, bring 2x over to the other side. So I subtract it. Y is less than or equal to negative 2x plus 8. Oh, did I have to flip the inequality? No. When do I flip inequalities? Multiply or divide by a negative. All right. So let's see. Information I can gather about this. The slope is negative 2. The y-intercept is 8. It's shaded above or below. Which way? Shade above, below. Below, because it is a less than sign and it's a y relationship. So also all of these lines I realize are solid lines because they all have the equal to portion for the inequality there. So let's see, let's look at this last equation or inequality. X plus 3y is less than or equal to 6. To put that in sloppy intercept form, we'll subtract x from both sides, and I'll get 3y is less than or equal to negative x plus 6. What should I do now? Divide by 3 both sides. Do I have to flip it?
No.
No, because it's positive. So I get y is less than or equal to negative 1/3 x plus 2. Yeah, I guess I'll put these equations in nice little boxes here for us. Why not? So let's see, what's the slope? Sloppy Joe. Negative 1/3. B is equal to 2. Shade above or below? Below. So let's try to get a visual picture of where this is. So let's see. So my first two lines are a vertical at 0, a horizontal at 0, and those are shaded above or to the right. These two lines have positive y intercepts and negative slopes and are shaded below. I think my graph is going to exist primarily in which quadrant? It's going to be in the top right quadrant. Top right quadrant. So you guys can just draw a quick little, you've seen my little graphs before. I just do this and little tick marks. You know what I'm saying, right? Just try to make your tick marks evenly spaced.
Just wait, don't start yet.
Well, it's all right. You can catch it later. Don't worry. It's fine. I'm waiting. So let's graph these. X is greater than or equal to 0. Where's that going to land? Actually, I'm going to make this one purple.
Oh, did you do it like that because you know it's all going to be in the...
Yeah. I tried to pre-plan my window a little bit. Yeah. Since my largest y-intercept was 8 and had a negative slope, I figured it all fit there, right, Kirsten? I didn't have to go up to like 20 or nothing like that. So let's see. X is greater than or equal to 0. What's that line look like?
Wait, so there's going to be two things? There's going to be two, like...
There's going to be 4 separate equations on this.
Whoa.
Yeah. So x greater than or equal to 0, what does that look like?
It's vertical, it's at 0.
Yep, so that would be a solid line like this. And shaded to the right. I'm not going to shade it just yet because I anticipate having a bunch of shading going on. So I just know that it's shaded to the right. Let's see, we'll make this y1 orange. Y is greater than or equal to 0. What's that look like?
Horizontal at 0.
Horizontal at 0 and shaded above. Yeah, multiple colors is certainly nice for this lesson. Let's see, y is less than or equal. We'll make this one green, why not? Y is less than or equal to negative 2x plus 8. That's a y-intercept at 8, a slope of negative 2. So down 2 and over 1. Okay, so something like this right here. Down 2 over 1, down 2 over 1, down 2 over 1. And this is solid. Something like that. And like that. And this one's shaded below. So far, what does our common shaded region look like between these three? Yeah, it's like just this triangle here, right? It's above this one, it's to the right of that one, and it's underneath this one, right? Something to that effect. So let's graph our last line. I might put dark blue for this one here. My little key here, I'm labeling this. Negative 1/3 x plus 2, so that's a y-intercept at positive 2. And a slope of negative 1/3, so that's down 1 over 3, right? And then down 1 over 3 again. So let me just get rid of my arrows here. And like so, that's a solid line.
Oh, why did you shade it in?
Why did I shade what in?
Dang it.
What? What do you mean? I didn't shade anything yet.
You surely shaded it in.
Oh.
You shaded it in and then you just...
Oh, yeah, I undid it. Yeah. So this is shaded where?
In that little corner right here.
Shaded below. Right, the green one was shaded below, so it's only actually a constraint for this little portion here. This one was shaded above, and this one is shaded to the right. So our common shaded region is this all right here.
So not the top that I shaded.
Correct.
Cool.
You try and take it.
Right, so here's our awesome shaded region here. Now, when you have a shaded area like that, composed of different boundaries, so to speak. Some of these boundaries could have been dotted lines and stuff. There's actually a name for that. It is called it's a crazy name, a polygonal convex set. You don't have to write that down, but you will see that term show up within your homework. They might say, graph the polygonal convex set, something like that. But that's what they're referring to. It's a little polygon, and it's a set of different inequalities or boundaries or constraints that ended up defining where that occurred. Now, so that is technically how we graph a system of inequalities. And if I wanted to do a check, I could pick a point within this shaded region, for instance, the point 1, 1, and I would expect that this point would work in all 4 of the inequalities. If it failed, that means I would have done something wrong. So let's say, for instance, what if I did think that this part of the triangle was in my solution? This would have worked in 3 of my equations. It would have worked in this one, and this one, and would have failed in the last one. All right, so just because you'd pick a point that checks out for one of them doesn't mean it will check out for all of them. Question, let's see if you guys get this concept. This point right here, which equations would this point work in? The first 2, because it's to the right of this and it's above that, but it is not less than this or less than that, right? So yeah, it would work in the first 2. So I just want to point that out. In all of these little cross sections of space, you could actually find points that would work in 1 or 2 or 3 of your inequalities, but not all of them. And it's just in the polygonal convex set that we would have the full set of solutions. So let's foreshadow what we're doing tomorrow. You do have problems tonight like this as well, where we're actually going to say, okay, so let's say I had all these inequalities and I found these solutions, but I want to find which of these solutions ends up being optimal for some situation. All right, let's say, hypothetically, let's say X was the number of chairs that a company manufactures, and let's say Y was equal to the number of tables. All right. And so these are all possible combinations of chairs and tables that the company could make, considering whatever limitations we defined on it. And I want to figure out which of these combinations will give me the best possible profit. And let's say I gave you a profit equation where I said P of X comma Y is equal to 100X plus 60Y. All right, so this would be what's called a profit equation.
So wait,
And what that would tell me is that I'm earning $100 for every X, all right, and $60 for every Y. Obviously, this probably is not a realistic problem because I would hope that they'd earn more money off their tables than chairs. But, so then you could analyze this sort of equation based on our constraints and say, all right, what point in this system, or multiple points perhaps, would give me the most profit? Now, question, do you think it would be a point like 1, 1?
no.
Why not? Like, just thinking out loud. Why? Or would you have thought it would have been like a point like here or here? Now, if you think about it, if I'm looking for a point that's going to give me the maximum value for this, it's probably not going to occur in the middle of the set, right? Because those aren't very extreme points. It's probably going to occur on the outermost edges somewhere is where the maximum would occur. I think you'd agree, right? That's where the most extreme values are, right? And the most extreme points of my edges are which points?
Like,
The corner points?
Yeah, the corner points, exactly. And it turns out that those corner points will typically be one of our maximum or minimum values. All right, so if I label those A, B, C, D.
So we have to do that that we did math 3.
I'm not entirely sure what you're talking about. But let's write this concept down. This is called the Vertex Theorem. I guess I should label it first. Vertex Theorem. And I'll give you a chance to write this. So the Vertex Theorem says that the maximum or minimum value of some function, f of x, y equals blah, 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 on a polygonal convex set, that's referring to our shaded region, right, occurs at a vertex of the polygonal boundary.
Wait, so we write both of those now?
You didn't have to write down the top one there. That was from earlier. Right, and it's based on the logic that I just walked you through. Mathematically, it's been proven, but I think logically it kind of feels like it makes sense. Yeah, it's got to be one of the most extreme points on our set of solutions, and those are going to occur on the boundaries. And the most extreme points of the boundaries are going to be on the vertices of the figure. And then I guess I'll write a note here, is that if there is a tie between 2 points or 2 vertices, any point on the line through those vertices is equally optimal. Man, that's such a cool way to say it. Wouldn't happen often that there'd be a tie between 2 of the vertices, but it can. And when that occurs, basically that whole edge of the boundary that connects those 2 vertices would be equally optimal for either a maximum or a minimum. Sometimes we'll be looking for minimums, so it doesn't necessarily mean you want to maximize profit. Maybe you want to minimize cost or minimize casualties due to your chairs and tables that you manufacture, right? That would probably make sense, right? You want to minimize the number of people that die in tragic dinner time accidents using your chairs and tables. I don't know, maybe, right? Sometimes you want to minimize things. But what's nice about this is actually on the threshold of learning this concept that is a non-calculus type of optimization in mathematics. And this works for at least 2 variables anyway pretty well with the current technique that we're looking at. So let's go back and look at this little problem and see if we can figure out which of our vertices would give us the optimal solution. Optimal solution. So, all right.
No. Okay.
So, all right. Let me take a snapshot of this actually. And I'm going to give some room for myself to continue working. So this is what I've got. I've got my profit equation. I labeled my points A, B, C, D. What is the coordinates? What's the ordered pair for point A?
0, 0.
0, 0. And I believe you could read that easily off of the graph, right? I don't think that's impossible. What are the coordinates for point B?
2, 1.
0, 2.
Oh no. I tried.
What are the coordinates for point C? Huh.
3.5.
Yeah, it lands somewhere in there, but I'm not actually certain where it lands. Huh. Well, let's ignore that for a second. What about point D?
4, 0.
That does actually land at 4, 0.
Oh.
Now, point C, I'm confused about. Point C is composed of the 2 equations, the 2 diagonal equations. The green one was the 2x plus y is less than or equal to 8. And the blue one was originally the x plus 3y is less than or equal to 6. And if I want to find the intersection between those two lines, how could I do that? How could I find the intersection of those two lines? Because it doesn't land at a nice point for us. Solve the system of equations algebraically. All right, because I don't know where that intersection occurs. So in our case, I would have to solve the system that makes up those two lines, which are those two equations. And since I'm just looking for the intersection of those two lines, I could actually do that just using those equations like so. So let's say I've got 2x plus y equals 8, and let's say I've got x plus 3y equals 6. So how do you guys want to solve this? It's been a while. You want to use substitution, elimination, matrices, Kramers? Kramers? Let's use Kramers. Why not?
Why would you say that?
So let's see. The determinant of matrix A would be the determinant of 2, 1, 1, 3. So that's 6 minus 1 or 5. All right, that's my denominator. X numerator would be the determinant of, I would replace the x column, I'm sure you guys remember, with the right-hand side. Oh, of course. But of course. 8, 6. Okay, okay. So 8 times 3 is 24, minus 6 is 18. I'm just trying to, this is the part that we already know how to do. Find y numerator. I would replace the y's column with the 8, 6 this time, right? Classic. And 2 times 6 is 12, minus 8 is 4. So that means x is equal to 18/5 and y is equal to 4/5. Right? So you could have solved this using any of our previous techniques that you're all masters at. But I just wanted to point out that if you have an intersection as a vertex of one of your, of your polygonal convex set, and it doesn't land right on the grid, then you should solve the system of the equations that made up those two lines. So 18/5 and 4/5. Let's see, 18/5, what's that? 3.6. And 4/5 would be 0.8, something like that. So you can see, okay, that does actually make sense for point C.
Can we just keep those fractions? I thought fractions were.
Yeah, I like fractions as well, but in this case, I just want to point out that those aren't even approximated decimals; those are exact. But yeah, you could have used fractions as well. So, all right. Now, what we're going to do with these?
Why does this problem keep going?
Don't worry about it. Don't worry about it. We're just about done. I need to figure out which of these is the best. All right. And what was my equation? P of xy
It's 0.
is equal to 100x plus 60y. So all I'm going to do is plug in x and y for both of these and figure out which one gives me the optimal solution. So let's see, 100 times 0 plus 60 times 0, that's equal to 0. That's not very much profit. And if you found that to be the optimal solution, that would be like, I'm sorry, bad news everyone, we're shutting down our chair and table factory, you're all fired. Like no Christmas bonus this year.
Whoa.
Yeah, like, so hopefully that's not the case. We're not going to shut down the factory. That's not our optimal profit. Whew, that's scary. Let's see, 100 times 0 plus 60 times 2. That's $120 profit. Yay! 100 times 3.6 plus 60 times 0.8. Oh, I just plugged that in way wrong. I think I got 84 for that. I believe. I believe. And let's see, 100 times 4 plus 60 times 0. That's just 400.
Yeah, well,
We have a winner, yeah. So 4-0 in context of the problem would say make 4 chairs.
wait, how is 100
That's what I was gonna say.
3.6?
100 times 3.6. Oh, that's 360. I thought it was. Good call. Good call. You got me. You got me.
Yeah, we did.
Yep. That was the one bit of math I did in my head, and I shouldn't have clearly. That's 360
Yeah,
plus 60 times 0.8. Good save. 408. Oh, wow.
We have a new winner.
We have a new winner. Oh, that's great news for us as well. You know why? Because I don't have to shut down my my tables division.
Number 84 and 4 we over.
Yeah.
Although maybe this problem doesn't make much sense in this context. Make 3.6 chairs and 0.8 tables. Right? Yeah. Yeah. Small family right there. Yeah. They would love this table and chair collection. But yeah, that's the idea behind this is you graph the system, and if we were somehow going to represent it as a polygonal convex set and wanted to optimize an equation, we would do so by just finding the coordinates of those vertices, plug them in, figure out which one gives me the best. Thanks for backing me up on that error there at the end there, friends. Bye-bye, buddies.